This section talks about power series solutions to differential equations. But before we do that, from Calculus 2, we learned how to write a power series representation for a given function. So if you have a function e to the x, for example, its power series is the sum of x to the n over n factorial, if you guys remember this. And if you write it down by taking n equals 0, 1, 2, 3, you get 1 plus x squared over 2 all the way. Same thing happens for 1 over 1 minus x, same for sine, cosine, tan inverse. Those are the ones that we use the most. Of course, there's more than that, but those are the ones that we use a lot. Keep in mind, sine x is an odd function, so that's why it's you see an odd power there with the sine. So when it's sine, there's an odd power, because any odd number can be written in the form of 2n plus 1. Cosine is an even, that's why there's an even stuff there. And on the right, far on the right side, there's radius of convergence. R equals 1, infinity, 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 and 1. So this means it converges everywhere. So first thing is convergence. What does it mean to say convergence? What does it mean?
Finite.
It converges to a certain value. It doesn't, it goes to a certain value. It converges. It's heading somewhere. If it's not convergent, we say diverges. A series diverges or a sequence diverges. So what we're going to learn in this section is we are going to learn how to use power series. So what is a power series? Do you guys remember? It's x minus, say, x0 to the n, and there's a sub n there where n goes from 0 to infinity. Is a power series around x equals 0 or x0 or x node or a, some people call it a. So we're going to use or find the power series solution for a differential equation. So basically we need to write the solutions of a differential equation in a power series form. Power series form. So at the end, when you find the general solution for the differential equation, it will be a power series. We'll say this power series is the solution for this given differential equation. To start with this one, with something like this. So we start with this by introducing a theorem, introductory theorem. If P or P of X and Q or Q of X are analytic, well, before we say are analytic, if P and Q in the differential equation y w prime plus P of X y prime plus Q of X y equals f of X are analytic, and I will explain what analytic means, for x minus x0, the absolute value, less than r, then the solution solution of the above differential equation can be represented or found using power series, presented by a power series. So now what is analytic? What is analytic? So first let me explain analytic, and we're gonna not use it a lot in this section, but in the next section, yes, we will. Analytic means all derivatives all derivatives of p of x and q of x exist and the functions could be expanded or represented by a convergent power series. That's what it means. For all x, of course. For all x within R of fixed number x0. That's what this means here. That's what this means. Now that equation, let me call it equation 1, the differential equation. We say every solution of that equation 1 is itself analytic. That's what analytic. Now, in the previous sections, we learned how to solve differential equations, using some approach. And the only condition that we wanted to have is that P and Q must, so from before, P and Q must be, both are continuous from before. P and Q must be continuous. But now we need more conditions. They have to be analytic. We're not going to check it for this section, these conditions, but they have to be analytic, means P and Q, or P of x and Q of x, they have to be analytic for what? To guarantee a general solution. And again, to repeat the stuff, and the solution, of course, general solution for equation 1, and the solution can be found in a form of a convergent power series. So now this is where we start. The first thing I'm gonna start here to explain this, or how this works. We're going to start with a differential equation to ask us to solve it. Now, one thing notice about this differential equation has constant coefficients. It makes it easier to work with, and it's not difficult to solve this. But if you like to find, on the side, what is P of x here? There's no y prime term, so P of x is 0 and Q of x is 1, is the coefficient of y. Those are really analytic. So how do we use power series here? Always we start with y equals, or y of x equals the sum of an xn as n goes from 0 to infinity, like so. That's how we're gonna start. Always, all the differential equations with the same start. You can call it y or y of x. And this one, if you want to write it down, it's a sub 0 plus a1x plus a2x squared plus a3x cubed all the way forever. Notice something about this. To find the solution y, or y of x, Some people call it YP, or some people could write YT for trial as a trial solution to this. It doesn't matter what you want to call it. But in order for us to really find the solution to this differential equation, we're going to use this y equal the sum an xn, and then try to find all these coefficients a0, a1, a2, a3, and substitute them in here to be able to solve for that differential equation. So to do so, from that y equals the sum an xn, as n goes from 0 to infinity, we can find y prime. How do you find y prime? Well, you find the derivative of x to the n, you bring n down, subtract 1 from the exponent. That's y prime only. But wait a minute, if you happen to substitute n equals 0 in here, what happens? That kills the whole thing, as it happened with Albert. So it kills everything. So now what you can do, you can drop that 0 thing and make it start at 1, because the n equals 0 term is nothing. So now this is y prime, and then I still need to find y double prime, because the differential equation has y double prime, and y double prime equals the sum n goes from 1 to infinity, n times n minus 1 a sub n x to the n minus 2. So I found them, and then now we substitute into the given differential equation y double prime plus y equals to 0. So y double prime is the sum n goes from 1 to infinity, n times n minus 1 a sub n x to the n minus 2, plus y is the one we started with, an xn, n goes from 0 to infinity, and this is given equals to 0. No, it shouldn't start at 0, the one on the first one. It's at 1. Well, at 2 even, because 1 doesn't do anything here. That's at 2. Now, remember, these are convergent series, the first one and the second one, both of them. But in order for me to kind of combine them together, I need two things here. One, the x to the n, they should match. There's xn here, there's xn minus 2. And the other thing they must match are the indices, where the indices start. Notice one of them starts at 0, one starts at 2. What am I going to do here? Well, different people will approach it differently. You can use any approach you like. It's all will get you to the same result. You might find different series, but the final answer will be the same. So how do we get to change them? First, I like to change the exponents, make them match. Okay, and how do I make them match? I come to the first exponent here, and I make sure whatever I have here, I assume it's k. What I have here, I also assume it's k. But this k is in the first series, the other k is in the other series. So from here, you can solve for n. It's k plus 2. So I'm going to change everything from n to k. And the other one, n is just k. There's nothing to do here. So let's see what happens. Watch. Instead of n, I'm going to replace it with k plus 2. So k plus 2, like so. So I substituted n equals k plus 2, and I'm going to do the same thing here. K plus 2 minus 1, k plus 1, a, and replace n with k plus 2. X, replace n with k plus 2 minus 2, that's k. There's infinity here. And in here, I'm going to replace this with k plus 2 equals 2, so k equals 0. See, k starts at 0. Plus, remember, n equals k equals 0 to infinity. A sub k, x to the k. All this equals 0. Notice the indices, they both start at 0. and x to the k both match. Looks good? This is called shifting, like you shift something like 2 units to the left. Okay, so now our focus is on this. Now remember, these two series are convergent or converges. So this way, this means we can add the terms one by one. So if you take k equals 1 for each and add them up, plus k equals 1 for each one, add them up, k equals 2, k equals 3, and add everything. You're allowed to add term by term. Another way to do it is, especially since they have the same limits or bounds or indices, you can go from k to 0, k equals 0 to infinity, and you can write the k plus 2, k plus 1, a sub k plus a sub k plus 2 plus a sub k, and factoring out x to the k. So you can combine them into one series and factoring x to the k out. Now, in order for this sum to be identically equal to 0, this one, we don't take this one, we don't just assume always x to the k is never 0. Even if you take k equals 0, that will be 1. It's not going to make anything. So in order for a sum of a series to be equal 0, this means all of its coefficients, they must be 0. So imagine, like, if we scroll back up for this one here, in order for this to be 0, if each coefficient here, a0, a1, a2, a3, if each one of these 0, then the whole sum is 0. So that's what we have here. So what we can do is we can take this part here must be identically equal to 0 in order for the sum to be equal 0. So let me rewrite that down. K plus 2 times k plus 1, a sub k plus 2 plus a sub k must equal to 0. And after we finish this, you will get the big picture what I'm trying to do here. Just to give you an idea, we're trying to find all the coefficients, a sub 0, a sub 1, a sub 2, to be able to go back and replace it back into the original series that we started with. So what happens here, we always solve, if there's a k plus 1 and k, we solve for a k plus 1. We solve for what comes next. So here, if you solve algebraically for a k sub 1, that's by subtracting a sub k and dividing both sides by k plus 1 times k plus 2, it will give me this. It will give me this. Now, if you take, remember, k starts at 0. So if I plug in k0 here on both sides, I'll get a sub 2 equals something negative a0 over some number, 2, right? Like, I'll get that. And if you take k2, not 1, I'll come back to 1, 2, that will be 4. Then you get negative a sub 2 over some number, 4 times 3 or something. So if you try to find a6, the even cases, a4 over 8 times 7. So notice what's happening. If I want to find a2 depends on a0. And then after you find a2, you can substitute it here. That will give you a4. If you find a4, you substitute, you get a6. So do you see how it builds itself? Like, from a0, I can find all the even subscripts, a2, a4, a6, all the way to a sub 2n. That's if I know a0. What happened to the odd case? What happened to the odd case? If I take k0, that's what I got. If I take k1, that will give me a sub 3 is negative a1 over 3 times 2. If I take the case when k is 3, that will give me negative a sub 3 over 5 times 4. And this can go on and on. Notice, to find a sub 3, I need a1. As soon as I find 3, I can get 5. And as soon as you get 5, you get a7. So you can see this equation that we got depends on two things, a0 and a1, that we need to find. Do I have a0 and a1? I don't have a0, I don't have a1. So what we say, we pick a0 to be arbitrary, any constants, then what we get is a2, which is negative a0 over 2, or 2 times 1. a4, the one I found, is negative a2 over 4 times 3. You can leave it like this, or let me try to write everything in terms of one constant, which is a0. So if I substitute this in here, that will give me negative, negative, that will become positive a0 over 4 times 3 times 2. If I find a6, that's negative a4 over 6 times 5. And then I can replace a4 with a0 over 6 times 5 times 4 times 3 times 2. That's what I have so far. And this can go on and on. We do in a similar way. We look at the odd indices, a sub 3, as I did on the right side. A sub 3 is negative a1 over 3 times 2. A sub 5 is negative a3 divided by 5 times 4. But again, you can substitute that in here. That will get rid of the negative. That gives me 5 times 4 times 3 times 2. Right? And then a7, you can do the same thing for a7. So what do we get here? We get y equals, remember, a0 plus a1x plus a2 x squared plus a3 x to the third plus a4 x to the fourth plus a5 x to the fifth plus da da da. So what is a0? a0 stays the same. a1, what is a1? We don't know. a1 is arbitrary. Just keep it like this. Now, before I move on with this, one thing we can do instead of writing again and again, because it's a conversion series, I can split this into two different sums. I'm going to take the even sums, group them together. It doesn't work out this the whole time, it depending on the series. a6x to the 6 plus da 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 plus a sub 1 plus a sub 3 x cubed plus a sub 5 x to the 5th plus a sub 7 x to the 7th. So I broke it down like so. a0, as you know, there's nothing. a2, what was a2? Let me see if I have it here. A sub 2 was negative. It was negative a sub 0 over 2 times 1. The next one, a sub 0 over 4 times 3 times 2. Then minus a sub 0 over 6 times 5 times 4 times 3 times 2 plus da da da. That's for the first one. For the second one, a1 is random constant here. a3, we found a3 to be negative a1 over 3 factorial plus a1 over 5 factorial minus a1 over 7 factorial plus da da da, like that. And then watch something. First thing, in the first parentheses, we can take a0 out, and that will leave 1 minus 1. Oh wait, I forgot the x square, x to the 4th, x to the 6th, x to the 3rd, x to the 5th, x. I was just paying attention to coefficients. So that's x squared over 2 times 1. Notice 2 times 1 you can write as 2 factorial. X to the 4th, this is 4 factorial. X to the 6th, 6 factorial. Plus, same thing we do here. We take a1 out. That will give 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus da da da. So what did I get here? This is actually the solution. This is the solution for that differential equation. What is this about? This is in the form of some function. This is function called h of x. So a0 h of x plus a1, call it like r of x. So y is the sum of two linearly independent functions here. So it's the general solution for that given differential equation. Now, if you recognize what's inside the brackets, that would be the best that you can write it down. So if you want to write down, what is this 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and so on? Well, we can go back to the table we started with. That looks like it's a cosine. And the next one where it says x minus x cubed over 3 factorial, x to the 5th over 5 factorial, that means it's a sine. So I can go back down there and replace the whole quantity inside the first bracket with cosine x plus a1 sine x. So if you pick values for a1 and a0 for specific values for a1 and a0, we obtain y particular to that given differential equation. So there's an x missing in here in this part, but when I factor, there should be an x there. So now it's fine.
Yeah.
So now what we do is we try to I'm gonna try to solve y w prime plus xy equals to 0. Notice this equation, I'm gonna use power c's again. It has non-constant coefficient. Non-constant coefficient. So again, how do we start with this one? Well, we start y equals the sum of a sub n xn, n goes from 0 to infinity. And again, we need to find y prime, which is the sum n a n x to the n minus 1. N goes from 1. Remember, n starts at 1. And from there you can find y w prime. N starts at 2 to infinity. N times n minus 1, a n x to the n minus 2. So we found y prime, y w prime. If the equation has y triple prime, you have to go more and get y triple prime. So now we substitute y w prime into the given equation. So it's the sum n goes from 2 to infinity. N times n minus 1, a sub n x to the n minus 2 plus x times, this is the a n x n. N goes from 0 to infinity, and this is equal to 0 from the given differential equation. The first thing I see here that is kind of like, what is this doing here? There's an x there. What we can do, because this series converges, we can, if you write this out, then you can multiply x by every single term. In another way to do this, instead of writing that down, is just bring it inside. When you bring it inside, what changes is kind of, you're multiplying now x times x to the n. So that becomes x to the n plus 1 by adding the exponents. Okay, so now what I'm going to do is, first, as I said, I want to get the exponents to match, this and this to match. Different people have different ways of approaching this. So what I do personally, I just take whatever I have there, I take it to be k. So you can get n from here, k minus 1. Same thing. N minus 2 is k. So n is k plus 2. Now we convert everything from n into k. Instead of n, I'm going to put k plus 2. K plus 2 minus 1, k plus 1. A sub k plus 2. X to the k power. Plus. So instead of n, put k plus 2. So you get k plus 2 in here. K plus 2 equals 2. So k starts at 0. Plus a sub k minus 1, x to the k. N equals 0. If you put n equals 0 here, k would equal to 1. K would equal to 1. Notice something. So the x to the k match now, but the indices don't match. They don't match. So how are we going to get the indices match? Watch this step. Not difficult, but watch it carefully. We look at k equals 0 and the other one k equals 1. We start with the smaller value, which is the 0. And then we take k equals 0 and substitute it in here. So what do you get? 0 plus 2, 2 times 1 times a sub 2 x to the 0. And then make the series now starts at 1 because k equals 0 term, I took care of it. Plus, keep this the same. So what do we get here? 2a sub 2 plus, let's keep this the same. Keep this the same. It's good. So now these two series, they have the same x to the k term, and they both started at k equals 1. They both started k equals 1. Let's keep this the same. Now I can combine these into one series. K plus 2 times k plus 1 a sub k plus 2 plus a sub k minus 1 x to the k equals to 0. Again, in order for this to equal to 0, to be identically equal 0, all the coefficients, they must equal to 0. So the first thing, this should be 0. That gives me a sub 2, 0. That's the first one. And k plus 2 times k plus 1, a sub k plus 2 plus a k sub 1 equals to 0. Again, we are going to solve for a sub k plus 2. That's a negative a sub k minus 1 divided by k plus 2 times k plus 1. Okay, so now we can pick values for k. So when k is 1, what do we get? We get a sub 3 equals negative a sub 0 over 3 times 2. If we take k equals 2, what do we get? A sub 4 negative a sub 1 over 4 times 3. You can start like this first. K equals 3, you get a sub 5 equals negative a sub 3 divided by 5 times 4. No, this is 2 here. K equals 4. What we get? A6 is negative a sub 3 over 6 times 5. K equals 5. A sub 7 is negative a sub 4 over 7 times 6. The more values you pick, the better. So you want to, if you want to try to find patterns in here. A sub k is negative a sub what? 5 over 8 times 7, or 6 plus 2, 8 times, yes, 8 times 7. Now the first question that comes to mind is there any pattern here? So please share that over the chat if you find something out. First thing I see that, don't forget that the circled one, a sub 0 is 0. So this is 0. Because a5 0, a8 is going to be 0. Right? Those are zeros. So that will motivate me later on. That will motivate me to group A2 together with A5, A8. Do you see the pattern? It goes, the indices is adding up three more. The next one would be A11. The next one A14. So that's one thing I noticed. Any more? Anyone notice something? Notice yes, we'll come to the arbitrary part, but another thing we notice is it starts with A3, so A3 depends on A0, right? A0, and A6 depends on A3, and I'm expecting the next one, A9, to depend on A6, so A9 depends on A3, so it goes up by 3s. Next one, A4 depends on A1, and A7 depends on A4, so they go up by 3 as well. So that gives me an idea which terms to group together. So I'm gonna start writing that down. Y, the solution. Remember, I'm gonna group A0 plus A3 x cubed plus A6 x to the 6 together from the original series, plus I'll group A1, A1x, A4x to the 4th up by 3, A7x to the 7th. I group them together. Plus I grouped A2x squared, A5x to the 5th, A8x to the 8th. And let's see what we get here. But since, remember how I said A3 depends on A0 and A6 depends on A3. So maybe I can get all these A3, A6, A9 in terms of A0. Right? So let's go back up and look at A3, A6. See if we can find some relation here. A3. So A3 is A0 over... nothing can be done here, maybe 3 times 2 for now. You can write that as 3 factorial. But if you look at A6, let's replace A3 with its negative A0, so that becomes positive A0. And in the bottom you get 6 times 5 times 3 times 2. See, the factorial doesn't work here because 4 is missing in the denominator. I can't say 6 factorial. So, but I was able to rewrite at least, let me put a bracket, A0, instead of A3, it was negative A0 over 3 times 2. And A6, I just found it A0 over 6 times 5 times 3 times 2. And minus, this can go on and on. Plus, that's the first one. Next part, A1, A4, A7. Let's try to find A4. It's already given as negative A1 over 4 times 3. Now, A7, there's a negative here. Negative with negative, that become positive. 7 times 6 times 4 times 3. Do you see how the 5 is missing? So let's put these two in there as a function of A1. So it's A1x. Instead of A4, we replace it with, if I'm not missing, 4 times 3 like that. Plus, the next one is A1 over 7 times 6 times 4 times 3. Because the fifth term was missing, yes, and the 2 missing. Minus some other terms. Plus, the next one, guess what? This is all 0. because a2 was 0, a5 0, a8 0. So now we can take a sub 0 out. That will give 1 minus 1 over 3 times 2. Oh wait, I forgot the x's again. So x cubed, x to the 6th. Here we have x to the 4th, x to the 7th. So x cubed plus x to the 6th over 6 times 5 times 3 times 2 minus da 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 plus the next one is a sub 1 out, x minus x to the 4th over 4 times 3 plus x to the 7th over 7 times 6 times 4 times 3 minus, and that would be the general solution, because I don't know any of these that can be rewritten. They can be rewritten like in terms of factorials or one of those trigonometric functions or ax or natural log of x or any kind of like a representation of power series as a function. So that's we can say that. Notice how y I was able to write as a0 plus a1 r of x, so h of x and r of x. So it's a combination, linearly independent functions here, as you can see, and that would be the general solution to that given differential equation. Next, one other example. Solve this differential equation, y prime plus 2xy equals to 0. Should we do it together? Okay. So we start with letting y equal the sum a n x to the n. From here we find y prime n a n x to the n minus 1. But again, you can put n1 here. Then substitute. So n a sub n x to the n minus 1 and goes from 1 to there, plus 2x and goes from 0 to infinity, a n x to the n equals 0. Notice something. I see the 2x first. So the first thing comes to mind is to bring it inside because it's a conversion series. 2a sub n x n plus 1. The next thing I want to do is match the exponents. Match this and this. So let this be k. So n equals k minus 1. Let this be k. K plus 1. So what happens here? Instead of n, I'm going to put k plus 1. A sub k plus 1. X to the k. So n minus 1 is k. So that's k equals 0. 2 sub a sub k minus 1. X to the k. N equals 0, so k starts at 1. Similar case to the previous example. We take k equals 0 first in this one. That will give us a sub 1, basically. A sub 1, right? A sub 1 plus the sum where k goes from 1 to infinity. Then keep a1 the same. Combine these. K plus 1, a sub k plus 1, plus 2 a sub k minus 1, x to the k. All that equals to 0. Now, in order for this to be 0, this has to be 0 and this must equal 0. So a1 is 0, keep that here. And k plus 1, a sub k plus 1, plus 2a sub k minus 1 equal to 0. So we need a sub k plus 1, which is negative 2a sub k minus 1 over k plus 1. So this is the equation that we're going to be using to do this, to get what we need. So if you take k equals 1, you get a sub 2 equals negative 2a sub 0 over 2. So it will depend on a0. So a0 is the arbitrary constant. So this simplifies to negative a sub 0. Then you find a sub 3, which is negative 2a sub 1 over 3. A sub 4, negative 2a sub 2 over 4. A sub 5, negative 2a sub 3 over 5. A sub 6, negative a 0 over 6. A sub 7, negative, why did I put a 0 here? If you calculate it, it's negative 2a sub 5 or 4 over. So keep in mind, this is for k equals 2, this is for k equals 3, this is k equals 4, k equals 5, and so when you put the 5 in, you get 6 in here. And then k equals 6, so you're going to have 7 there, a sub 5. And let's see if we can find a pattern here or something that would help us to make it easier. Okay, let's go back up. A3 depends on A1, but A1 is 0, so this is 0. Anything that depends on A1 or A3, this is 0. A5 0, so A7 0. So I can see the odd terms 1, 3, 5, 7, all of them are gone. All are zeros. Now A2 is in terms of A0, so I can substitute that in here. So here you can simplify negative 1/2. And instead of A2 you can put negative A0. So that's 1/2 A0, because A2 is negative. This one you can reduce, negative 1/3. A4 is 1/2 A0, or negative 1/6 A0. And this can go on and on. So then y equals A0 plus A1x plus A2x squared plus A3x cubed plus A4x to the 4th plus A5x to the 5th, A6x to the 6th. Notice something, all these odd ones are gone. So A0 stays. A2, what is A2? Is negative A1. So it's negative A0, sorry, negative A0x squared. A4 that we found earlier, it's A0 over 2 x to the 4th. Then A6, it's negative 1/6 A0 x to the 6th, plus we can take A0 out. That will leave 1 minus x squared plus x to the 4th over 2 minus x to the 6th over 6 plus etc. Notice, if you like to move further with this, this is 1 minus x squared plus x to the 4th over 2 factorial, x to the 6th over 3 factorial, because this is 1 factorial. And if you like, as one of you asked earlier, can I write this as the nth term for this? Yes, you can. It's easy to see, easier than the previous one. Let's see. There's an alternating in the sign, so there's a negative 1 to some power, say n, and n goes from 0 to infinity. That'll take care of the signs. In the bottom we have n factorial because that's a 0 factorial. And then we have all the numbers on the top, the exponents 6, 4, 2, and then 0. Those x to the 2n. So that would be the series for that. Note, I'm going to write the equation again, y prime plus 2xy equals 0. And just for fun, I'm going to solve this using separable. So dy dx equals negative 2xy. Bring the y down, negative 2x dx. Integrate both sides. You get natural log of absolute value of y is negative 2x squared over 2. So negative x squared plus c. So the absolute value of y is e negative x squared plus c, which is e negative x squared times e to the c. E negative x squared times t, or some random constant. So y is plus or minus t e negative x squared. And this can be rewritten as c e negative x squared. Right? That's the solution for this. Constant times this. But recall from the table that we started with that ex can be written as x to the n over n factorial, and goes from 0 to infinity. If you look in the table I started with today. And now look what I'm going to do. I see negative x squared, so I replace x with negative x squared. Negative x squared. And this can be rewritten as negative 1 times x squared to the n. So what do we get? E negative x squared equals the sum n equals 0 to infinity. Negative 1 to the n x 2 to the n over n factorial. If you multiply both sides by the c, the constant, we get c e to the negative x squared is c the sum. This is the y. That's exactly what we got, remember? Except c, besides c there's a 0 or something. Yeah, do you see? It's the same. Ta-da! Matches. No one said wow or something.